All right, I think we can go ahead and get started here. I just want to thank everyone for joining us for tonight's event. I'm Emily, I'm one of the events hosts here at Powell's. Before we begin, I just want to encourage you to check out the full lineup of our upcoming virtual events on our website at powells.com. One of the many events we're looking forward to is forest ecologist Suzanne Simard in conversation with OPB's Erin Scott about her new book, Finding the Mother Tree, on Wednesday, May 5th. If you don't already, please consider following us on Twitter, Facebook, and Instagram. Tonight, we are so honored to welcome Michio Kaku. Kaku is a professor of physics at the City University of New York, co-founder of string field theory, and the author of several widely acclaimed science books, including Beyond Einstein, The Future of Humanity, The Future of the Mind, Hyperspace, Physics of the Future, and Physics of the Impossible. He's a science correspondent for CBS This Morning and host of the radio programs Science Fantastic and Exploration. In his new book, The God Equation, The Quest for a Theory of Everything, Kaku tells the story of the greatest quest in all of science. When Newton discovered the laws of motion and gravity, he unified the rules of heaven and earth. From then on, physicists have been discovering new forces and incorporating them into ever greater theories. But the major breakthroughs of the 20th century, relativity and quantum mechanics, are incompatible. And so since then, physicists have been endeavoring to combine these two theories to ultimately tie all the forces of the universe together into one beautiful equation that would unlock the deepest mysteries of space and time. That epic journey is the story of Kaku's new book. So this event will also include an audience Q&A. There's a Q&A button at the bottom of your screen. If you don't see it, try clicking more. If you'd like to ask a question, please use that button. As well, if someone has typed a question that you'd also like to know the answer to, please upvote that particular question by clicking the thumbs up button. And perhaps most importantly, please consider supporting Kaku and Powell's by purchasing a copy of his new book from us. I'll be sharing a link to buy The God Equation, as well as his other books, in the chat a couple of times this evening. And I just want to thank you so much for joining us. It's such a pleasure. I'll let you go ahead. I think you've got a presentation.
Well, after such a great introduction, I can't wait to hear the speaker myself. Let me say that it's been a real pleasure to have a book tour like this. The book is now a New York Times bestseller. It just hit the bestseller list for the New York Times and Amazon just a few days ago. And I think that indicates that there's a hunger. There's a hunger out there. People want to know, is there a rhyme or reason to this great universe of ours? Let me say it's also been a pleasure working for the Discovery Channel and the Science Channel. I get to interview some of the greatest minds of science. And every time I interview these great scientists, I ask them the key question, the question of all questions, and that is there intelligent life on the earth? Well, I was watching the Kardashians on TV the other night, and I'm convinced that no, there's no intelligent life on this planet. But now let us begin a discussion of perhaps the greatest quest in the history of science, the quest for the Holy Grail. Is there a unifying theme, a paradigm, a principle that allows us to explain the vast diversity of the entire universe? That is the God equation, the quest for a theory of everything. I first heard about this when I was 8 years old. A great scientist had just died, and they published this picture around the world. It's a picture of his desk, and the caption said, "On this desk is the unfinished manuscript from the greatest scientist of our time." Well, I was fascinated by this story. Why couldn't he finish it? He could ask his mother, right? Why? Why couldn't he finish? What's so hard that a scientist cannot finish a theory? Well, I went to the library and I found out that this man's name was Albert Einstein. And I found out that he was working 30 years chasing after an equation that would allow him to, quote, read the mind of God. Well, I was hooked. I was fascinated. I had to know everything about this man. So when I was in high school, I decided to build an atom smasher, a particle accelerator. I asked my mom, Mom, can I build an atom smasher in the garage? And my mom said, Sure, why not? And don't forget to take out the garbage. Well, I took out the garbage and I assembled 400 pounds of transformer steel, and I built a 2 million electron volt betatron particle accelerator in the garage. Every time I turned it on, I would blow out all the circuit breakers. My poor mom, she'd say to herself, why couldn't I have a son who plays baseball? Why can't he play basketball? And for God's sake, why can't he find a nice Japanese girlfriend? Well, I dug into this and I found out that for 2,000 years, the greatest minds of history wanted to find this God equation, a single theme that would explain everything around us. Aristotle thought that air, water, fire, earth could explain everything around us, but Democritus thought it was atoms. And Pythagoras here said, no, 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 none of the above. The unifying theme of the universe, said Pythagoras, is music. Only music has the richness to explain the vast diversity of everything we see around the universe. Pythagoras noticed a lyre string one day. When you pluck a lyre string, the longer the string, the lower the note. He went by a blacksmith shop, and Pythagoras noticed that the longer the sword, the lower the note. So he said, aha, there's a mathematical principle, the mathematics of resonances. Each set of vibrations corresponds to a note. One note, one vibration shown here. Well, he founded a school, but it never went anywhere because, of course, that was 2,000 years ago. With the collapse of the Roman Empire, Europe fell into chaos, witchcraft, sorcery, magic, and all the dreams of the Greeks were lost. However, in the year 1666, the Great Plague hit London. London was locked down. One quarter of the population died in London due to the Great Plague. But there was a young gentleman who realized that his university, Cambridge, was shut down, so he went home. While he was home, he saw an apple fall, and then he saw the moon. And then he asked a question that changed world history. If an apple falls, does the moon also fall? In other words, it was Isaac Newton who unified the laws of the heaven with the laws of the earth. And in the process, discovered calculus so he could calculate the motion of Halley's Comet, the motion of planets, the motion of the universe itself. So the first unification was the unification of heaven and earth. And this initiated the Industrial Revolution. We could use Newton's laws to calculate mechanics, stresses. We could calculate heat. The steam engine. The steam engine was a direct consequence of Newton's laws applied to atoms. With the steam engine came locomotives. With steam engines and locomotives came factories. The Industrial Revolution, the greatest revolution in human history, set into motion because Newton dared to unify the laws of the universe. And then 200 years later, Faraday and Maxwell, they noticed that electricity and magnetism are two sides of the same coin. If you vary an electric field, you get a magnetic field. If you vary a magnetic field, you get an electric field. So, aha, they are two sides of the same coin. So Faraday and Maxwell unified them. Maxwell was a mathematician too. He said that if a changing magnetic field creates an electric field, if a changing electric field creates a magnetic field, the sum total must create a wave. He calculated the speed of this wave, and he had the greatest shock in modern times. Maxwell showed that the speed of the electromagnetic wave was the speed of light. In other words, this was light. That's what light is. It's a vibration where electricity and magnetism are unified into one wave. Well, after World War II, scientists then turned their attention to the nuclear force, and physicists began to smash protons apart. They thought that things would be simple because the deeper you go, the simpler things get. Nope. A zoo, a zoo of subatomic particles were discovered. J. Robert Oppenheimer, father of the atomic bomb, was so frustrated by this flood of subatomic particles that one day he said, quote, "The Nobel Prize should go to the physicist who does not discover a new particle this year." We were drowning in this zoo of subatomic particles, quarks, mesons, neutrinos, electrons, leptons, hadrons. It goes on and on and on. Well, by that time, a picture began to emerge of the presence of a God equation. First of all of biology can be expressed in the language of chemistry. All of chemistry can be expressed in the language of physics. All of physics can be expressed in terms of two theories: the theory of the very big, relativity, black holes, big bangs, and the theory of the small, the quantum theory, which makes possible lasers, transistors, computers. The problem is these two theories do not unify. It's like God has a left hand and a right hand, and the two hands don't talk to each other. How is that possible? Well, after many decades of smashing protons, scientists built the Large Hadron Collider, much bigger than the atom smasher I built when I was in high school. This is a machine hurling protons at 14 trillion electron volts. Geneva, Switzerland is where it's located. And an avalanche of particles was discovered with the Large Hadron Collider. But over the years, they were able to piece together some of the symmetries of these particles. Voila, the standard model, which is the theory of almost everything. It is a theory that works. It describes subatomic particles, but it is the ugliest theory known to science. 36 quarks and antiquarks, 19 free parameters that you can adjust, 3 identical generations of quarks. I mean, look at this mess. It's like taking an aardvark, a platypus, and a whale, scotch taping them together with a scotch tape, and declaring that to be nature's finest, most elegant evolutionary creation. Look at this mess. At low energies, it does work. But at high energies, maybe it doesn't work. Maybe that's a signal that there could be a higher theory out there. And 2 weeks ago, outside Chicago at the Fermi Lab, outside Geneva, Switzerland, where the Hadron Collider is located, they found a crack in this model. This model, thank God, has a crack in it, meaning that there are other particles out there, more particles, which hopefully can be rearranged according to the laws of music. Music, just the way Pythagoras envisioned it 2,000 years ago. If I have a super microscope and I could peer into an electron, normally you would see a dot. However, if the microscope is powerful enough, you would see a rubber band. A rubber band. And when it vibrates in a certain mode, we call it an electron. If it vibrates in a different mode, we call it a neutrino. So all the subatomic particles are nothing but notes on a single string. This unifies the zoo of subatomic particles. So in other words, physics is the melodies on the string where the notes of the string are particles. Chemistry is the melodies you can play on these strings. The universe is a symphony of strings, and the mind of God is cosmic music resonating through hyperspace. Well, just like Michael Faraday, you can express it in the language of field theory. This is my equation. I discovered this equation with my colleague, Keiji Kikawa, and it describes string theory. However, it's not the final theory. there exists yet another theory out there because this equation omits membranes. It now turns out, much to our surprise, that membranes can also coexist with strings. But for strings, this equation, my equation, gives you all the known laws of physics. So how do we test this theory? Well, as I said, in Geneva, Switzerland, outside Chicago, perhaps we can test it by looking at a deviation in the standard model. Also, dark matter. Surrounding the galaxy, there's a halo of invisible matter holding the galaxies together. If it wasn't for that, the galaxy would fly apart. Now, if any of you out there listening to my lecture ever figure out what dark matter is, if you ever figure out what dark matter is, then what should you do? First, you should tell me first. Then we can publish together and we'll share the Nobel Prize in Physics. We have maps of dark matter. Dark matter is invisible, so how can you have a map of invisible substance? Well, look at your glasses. Your glasses are also invisible, but you can see glass because light bends. Light bends when it goes through dark matter. That's how we know where it's located, and sure enough, it's like a halo surrounding the galaxy. If it wasn't for dark matter, we wouldn't be here, by the way. The galaxy would be unstable and fly apart. If we find dark matter in the laboratory, it could be the next octave of the string. We are the lowest octave. We're the lowest excitation of the string, but there are higher excitations, and the higher ones could be dark matter. So what can you do with this theory? You can also answer some of the deepest questions of the universe. You know, children, when they go to the science museum, they say, Mommy, Daddy, if the universe is expanding, what is it expanding into? And if there was a big bang, what happened before the bang? These are some of the questions that children ask. Is time travel possible? Are there wormholes or gateways through the universe? Is there a white hole that exists on the other side of a black hole? Are there other dimensions? Are there other universes? None of these questions can be answered using the old theory, the theory of almost everything. You need a higher theory, and that theory could be string theory. So let's talk about it. How do we test these theories? Well, in the future, the European Space Agency and NASA will launch LISA into orbit, Laser Interferometry Space Antenna. It'll pick up gravity vibrations from the instant of creation. Think about that. Baby pictures of the infant universe as it emerges from the womb. That's what this is all about. And maybe, just maybe, we'll pick up an umbilical cord connecting our infant universe to a parent universe. Because string theory predicts there should be other universes out there. And black holes, we photographed one last year. It was a shadow of a black hole. But what happens when you fall into a black hole? Well, in 1935, Einstein himself solved his own equations and found this. This is a wormhole. We physicists call it the Einstein-Rosen bridge. You fall in, like in a black hole, and you fall out the other side. It is a gateway. It is a passageway between universes. You can also perhaps have a gateway to your past, in which case it's a time machine. Now, of course, these are solutions of Einstein's equations, but how stable are they? Can you really go through a wormhole? Can you really visit a parallel universe? That requires a theory of everything. Now, you've seen this before. Over 100 years ago, there was a mathematician at Oxford University who knew about these wormholes. Mathematicians call them multiply connected spaces. Think of two sheets of paper, two parallel sheets of paper, and then make a bridge between these two universes. That is a wormhole. Well, Charles Dodgson was this professor of math at Oxford. He wanted to introduce this to children. But you see, he couldn't write under his name because he was an Oxford mathematician. So he wrote it under a pen name, Lewis Carroll. In other words, the looking glass is the wormhole. It is a gateway between two universes, giving us a new picture, a multiverse of universes. So our universe is a bubble, and the bubble's expanding, and we live on the skin of the bubble. That's called the Big Bang Theory. But string theory says there are other bubbles out there, other universes that maybe Lisa will detect as gravity waves in outer space. And then I know the next question you're going to ask me. The next question you're going to ask me is Elvis Presley still alive in a parallel universe? Well, yeah, that's the quantum theory. There's a certain probability that in another universe, Elvis Presley survived and is still belting out hits in another universe, but not in our universe. Sorry about that. This theory is bizarre because it actually predicts that the universe is 10 or 11 dimensional. Now, common sense says that there are 3 dimensions to the universe: length, width, and height. That's it, folks. But you see, people have often been curious about other dimensions. Edwin Abbott was a novelist. He wrote a novel about flatland, people who are 2-dimensional living on a sheet of paper. And these people said the 3rd dimension is a fiction. There's no such thing as the 3rd dimension, only forward, backward, left, and right. You know, when I was a child, I used to visit the Japanese tea garden in San Francisco where the fish are in a shallow pond. They can move forward, backward, left, right. And I imagined what it would be like to be a fish, to live in 2 dimensions. Anyone who talked about a 3rd dimension would be considered a crackpot, crazy to talk about a 3rd dimension. Well, today, we physicists believe, that we can't yet prove, that we are the fish. We spend our life in 3 dimensions, right? Not realizing that they are 4-dimensional hypercubes that you can envision on a computer, that even artists have been fascinated by the 4th and the 5th dimension, including Salvador Dali. Salvador Dali even incorporated the 4th dimension in his artwork. This is his famous painting, Hypercubicus Crucifixion. Many art majors don't realize this is a tesseract. This is an unraveled hypercube. And if you saw the movie Interstellar with Matthew McConaughey, in the final scene of the movie, Matthew McConaughey is floating in a cube. That's this. He's floating inside a tesseract. In other words, string theory is how the movie ends. It ends on string theory as Matthew McConaughey drifts in the 4th spatial dimension. Now, if you can burrow through space with a wormhole, why not go through time? Well, believe it or not, Einstein's equations allow for time travel. You see, Newton thought that time was an arrow. Once you fire it, it never deviates. Einstein says not so fast. Time is a river. It's a river that can speed up and slow down. The new wrinkle in all this is that maybe the river of time can have whirlpools in the river of time, in which case maybe you can resolve all the time travel paradoxes because the river of time can fork into 2 rivers, says the quantum theory. This means that when you go backwards in time to save Abraham Lincoln from being killed at Ford Theater, you've saved somebody else's Abraham Lincoln from being assassinated. Your Abraham Lincoln did die, but another branch of the river of time opens up. You've saved somebody else's, some other universe's Abraham Lincoln. So what's the problem? There's always a catch somewhere, right? The catch is, first of all, the energy. The energy necessary to go backwards in time far exceeds the energy of a DeLorean. We're talking about the energy of a black hole. So don't think that an inventor is going to invent a time machine in their backyard anytime soon. And of what use will this theory be besides time travel, besides understanding the other side of a black hole? Well, our universe is dying. Physics is a death warrant for the universe. The laws of physics, the second law of thermodynamics, says that in a closed system, everything eventually rots, decays, falls apart, and dies. That's why we die. We die because of the second law, because entropy, disorder, chaos, errors build up in our DNA, in our proteins. These errors accumulate with time. That's why we die. And the universe will also die. The universe will become a sea of black holes, dead neutron stars, and it will be very cold in the future. But there's hope. There's one and only one known way of escaping the death of everything, and that is to leave the universe. One day, trillions of years from now, we'll have enough energy to open up a gateway, a lifeboat, an Einstein-Rosen bridge, a wormhole to another universe. And then once we hop over to the other universe, then we can spend our time messing up that universe as well. Think about that. We'll have two universes to mess up. Well, that is my talk. However, I'd like to end on one note. I'd like to tell you my favorite Einstein story, and then I'll take questions. When Einstein was an old man, he was tired of giving the same talk over and over again. So one day his chauffeur came up to him, and the chauffeur said, "Professor, I'm really a part-time actor. I've heard your speech so many times, I've memorized it. So why don't we switch places? I will be the great Einstein. I'll put on a mustache, I'll put on a wig. You can put on my jacket and be my chauffeur." Well, Einstein loved the joke, so they switched places. This went along famously until one day, a mathematician in the back asked a very difficult question. And Einstein thought, oh, the game is up. But then the chauffeur said, "That question is so elementary that even my chauffeur here can answer it for you." Well, thank you very much. It's been a great honor to speak here today. And I'd like to just open it up for questions you may have about the universe and where it's going. Okay, let's now take a few questions that you may have.
Right. Well, that was wonderful. And I'm going to ask some of the questions now. Please, if you have more questions, put them in the Q&A module here. So the first one that I have for you is from an anonymous attendee, and it's, what are your thoughts on the recent findings with muons and a possible fifth fundamental force?
This is big news. This is really, really big news in physics. Outside Chicago, we have the Fermilab, the largest American atom smasher, and it looked for evidence of the magnetic properties of the muon. Now, the electron is, of course, the component of electricity. However, it has a partner, a slightly more massive partner that's heavier. It's called the mu meson or the muon. They measured the magnetic properties of the muon and bingo, they found a deviation. They found a crack in the standard model, indicating the presence perhaps of a new force or a new particle out there. This is good news, very good news, because that's exactly what string theorists have been praying for, hoping for all these years. The standard model is 50 years old. For 50 years, we've tried to find a crack in the standard model because it's so ugly, it can't possibly be the final theory. Why should God be so malicious to create such a bizarre, ugly theory? Aha, now we found a crack. So all the physicists in the world are looking very carefully at this new result to see what emerges. Maybe, just maybe, it's nothing but the next octave of the string. By the way, I should also point out that relativity is contained in the lowest octave, meaning that if Einstein had never been born, we would have discovered it anyway as part of the first octave of the string. That's how powerful string theory is, that relativity and the quantum theory are for free.
The next question I have for you is, can you tell us more about quantum entanglement and how it works?
Well, for you Star Trek fans out there, you know that Captain Kirk instantly communicates with Federation headquarters hundreds of light years away instantaneously. And that seems to violate Einstein's statement that you cannot go faster than light. However, when it comes to the quantum theory, Einstein got some things wrong. If I take two electrons and they vibrate in unison, and then I separate them, an umbilical cord, an invisible umbilical cord emerges connecting these two, so that if this is spin up, I notice immediately the other is spin down because the two spins cancel. This is called entanglement. Now, how fast does this information travel from one electron to the other electron? Instantaneously, faster than the speed of light. That's why Einstein hated the theory, because Einstein said nothing can go faster than light. So who was wrong? Well, Einstein was partially wrong. We've done the experiment. We can actually do these experiments now. And yeah, this information goes faster than light. But who has the last laugh? Einstein has the last laugh because this information is useless information. You can't send Morse code. You can't send the English alphabet. You can't send data. You can't send useful information, only gibberish. Gibberish can be transported from point A to point B. So Star Trek fans will be disappointed. However, there is one way still of communicating faster than light, and that is through a wormhole. And again, Einstein's equations only predict they exist, but how stable are they? That requires the quantum theory. Maybe when you enter a wormhole, it closes up on you. That'd be horrible if you're cut in half when you go through it, or it blows up on you. We don't know. That's why we need a theory of everything.
See, the next question comes from Robert Rendell, and it's, what is a quantum fluctuation?
Okay, we have Newton's laws of motion, which very accurately explain the motion of marbles, rocket ships, planets, and what have you. However, once you put the quantum theory in, then you have to sum over slight deviations because there's a certain probability that the atoms will vibrate in this direction, vibrate in that. Everything's vibrating. And so you don't know exactly the path of an electron anymore. These are called quantum fluctuations. Now, why should you care? The universe is probably a quantum fluctuation. You see, what is the net charge of the universe? Positive charges cancel negative charges in an atom exactly. The net charge of the universe is zero. What is the net spin of the universe? You calculate the spin of all the galaxies, they add up to zero. What is the net energy matter content of the universe? Gravity has negative energy, matter has positive energy. You add the two together, what do you get? Zero. In other words, the universe has the quantum numbers of nothing. No charge, no spin, no energy momentum, which means that the universe is probably a quantum fluctuation. In other words, these bubbles I talked about vibrate. And when they vibrate because of the quantum principle, one of these days, a piece of it peeled off. That quantum fluctuation then blew up to create our universe. In other words, where did the universe come from? It came from nothing, which in turn is compatible with the Bible, which talks about the mist. So Christian theologians like the idea that the universe itself came from nothing. In other words, it was a quantum fluctuation. A quantum fluctuation of what? Probably a parent universe.
Fascinating. And I'm seeing some questions in the chat here, and I think this one is sort of related to that one a little bit. So ask Rick's question here, which is, what role does faith play for you as personally in your work as a scientist? Not in a particular deity per se, but faith in a divine author.
Oh, you mean God? Well, first of all, let me say two things. One from Galileo, one from Einstein. Galileo once said that the purpose of science is to determine how the heavens go. What is the purpose of religion? The purpose of religion is to determine how to go to heaven. So, in other words, they're complementary. Science is about natural law to determine how the heavens go. Religion is about ethics, how to be a good person so you can go to heaven. Now, they're complementary. The problem emerges when some scientist begins to pontificate about ethics, or some religious person begins to pontificate about planets, stars, and natural law. If you keep these two domains distinct, they are complementary. Now, Einstein was asked directly about God. He said that he didn't believe in a personal God, a God that answers your prayers, spites the Philistines, give you that bicycle for Christmas that you prayed for. No, not that God. He believed in the God of order, simplicity, harmony. The universe could have been ugly. It could have been random, chaotic, but instead the universe is gorgeous. It's unified. It's simple. And Einstein therefore said, this is the God of Spinoza, the philosopher. And he said that the universe is like a library, this gigantic library that he entered as a little boy. And all he could do was read the first chapter, the first page of the first book. But in front of him was this incredible library of information. So he said, is it an accident? No, if it was an accident, we would have been chaotic. We would have been messy. The laws of physics, the theory of almost everything, can fit on one sheet of paper. It's a horrible mess, but it's one sheet of paper. We want to get it down to 1 inch, beautiful, elegant. It didn't have to be that way. It could have been chaotic. The universe could have been devoid of life. It could have been absolute zero temperature. It could have been a mist of electrons and neutrinos. But here we are in a gorgeous universe talking about this.
I've got another question from an anonymous attendee here, and it's, can you speak on how quantum theory ties into free will? Without it, all things would be predetermined based on strictly obeying the laws of physics and the current state of the universe, right?
Well, that's a heavy one. And if any of you out there ever figure this out, then tell me first. Let me explain. Newton and Einstein both believed in determinism. Newton said it best. He said the universe is a clock. It's wound up at the beginning of time. It's been ticking ever since due to his 3 laws of motion. That explains the motion of the entire universe. Einstein also had that picture. Einstein said, well, it's more complicated than that. Space is curved by matter energy, but it's also determined. Now comes Heisenberg and Bohr saying, not so fast. You don't know where the electron is. The electron could be here, there, simultaneously. Now that violates common sense. How is it possible that an electron can be 2 places at the same time? Well, get used to it. That's just the way the universe is. And so as a consequence, the quantum theory and relativity were at odds with each other. And determinism is, well, quantum theory says there is no determinism because there are only probabilities. There's a TV program on cable TV, Man in the High Castle. In that TV series, the Nazis won World War II. If you read the book carefully, the Nazis win World War II because an assassin killed Roosevelt, President Roosevelt, but the bullet could have misfired. Now, a bullet that misfires versus a bullet that fires correctly is due to tiny, tiny imperfections in gunpowder. And some of these imperfections are molecular. And quantum theory means that there's a probability that the assassin's bullet would hit or not hit Franklin Roosevelt. So what happens? The universe splits in half. One half of the universe is our universe, where the good guys win. In the other universe, the bad guys win, and we have Nazi flags and swastikas behind us. So determinism is not allowed in the quantum theory, because the quantum theory says everything is up for chance.
Nadine, and I think because you were talking about Man in the High Castle, I'm going to tie it into this question from Penny, which is, please tell us about any fictional media, TV shows, movies, books that you like or appreciate for how they present science.
Well, my favorite movie about aliens in outer space is the movie 2001, because the most efficient way to colonize the galaxy is not to send Captain Kirk hopping from planet to planet. That takes forever for Captain Kirk. No, you want a self-replicating von Neumann probe, a robot that replicates itself to land on the moon, make copies of itself like a virus, And these virus particles shoot out and colonize the entire galaxy just within maybe 100,000 years. Now, I get emails from people and they tell me, Professor, you're wrong. You're very wrong. The aliens are not there. The aliens are here. And how do they know? They tell me that they've been kidnapped. They've been kidnapped by flying saucers, so they know the aliens are here. Well, I have a word of advice for you. The next time you are kidnapped by a flying saucer, for God's sake, steal something, an alien chip, an alien hammer, an alien pencil. Steal something. There's no law against stealing from an extraterrestrial civilization. No law whatsoever. And then you can prove once and for all that the aliens are out there.
I love that. I'm just seeing one quick question from Carol here, which is, will this event be available on our website or YouTube? And it will. It'll be on our YouTube channel later this week. So tying into what you were talking about, it's splitting off into rivers, Dax asks, we experience time as an arrow, but does the future already exist?
Well, the short answer is no. Even in the quantum theory, the future is not knowable. Sorry about that. However, the quantum theory is a bizarre theory. It says that the universe, you can only calculate probabilities. So almost anything can happen, except there's a probability of this or a probability of that happening. For example, for our PhD students at our university, we sometimes give them the problem, calculate the probability that you'll wake up on Mars tomorrow. Now, any sane person will say you're not going to wake up on Mars tomorrow. But quantum mechanics says there's a probability. There's a probability given by Heisenberg that you will wake up on Mars tomorrow, and use the Heisenberg uncertainty principle to calculate the probability. When you do the calculation, you find out you will have to wait longer than the lifetime of the universe to wake up on Mars. So in other words, it is possible to wake up on Mars tomorrow, but the probability is against you. And the same thing with Elvis Presley. Is Elvis Presley still alive? Well, in another universe, perhaps he didn't take drugs. And as a consequence, maybe he was saved by somebody who rushed in to save him, in which case there could be a universe where he's still alive, belting out the hits. As amazing as that may seem, but we can't hear him. We cannot communicate with him because we're not coherent. We don't vibrate at the same frequency as that universe. Sorry about that.
Here's another one touching on that question of time, and this one's from Christopher. It says, to get back to the concept of time, can or does time move in more than one direction? In other words, backwards as well as forwards?
Oh, well, the short answer is no, and it's mathematical. You see, Einstein said that time is the fourth dimension, but that's not quite true. You can move freely in three dimensions. You can go forward, backward, left, right, up, down. Time, you can only go forward. You cannot go backward in time. So space-time is four-dimensional. It is four-dimensional, but the fourth dimension has an extra minus sign in the mathematics. That extra minus sign means you cannot go backwards. Now, globally, on a large scale, you can invoke general relativity, and then with a space warp or time warp, in other words, with a wormhole, you can in fact build a time machine. In fact, it was, I think, around 1949 that Einstein's roommate, Kurt Gödel at the Institute at Princeton, found a time travel solution within Einstein's equations. If the universe rotated rather than expanded, time travel would be possible. You could rotate around the universe and come back before you left. So Einstein was horrified that his equations allowed you to come back before you left. But in his memoirs, Einstein wrote that we can dismiss this solution because of physical reasons. In other words, the universe expands, it does not rotate. But if the universe rotated, then perhaps time travel would be ordinary. Now, a wormhole does that in miniature. So if you fall through a wormhole, in principle, you can go backwards in time. Now, how stable is that? We don't know. Stephen Hawking did the calculation, and Stephen Hawking said the time machine is unstable. It is a solution of Einstein's equations, but quantum corrections means it'll probably blow up. Now, I differ with that. I've done the same calculation. If you branch off into parallel universes, then you don't blow up at all. but it's a matter of debate still.
Fascinating. I've got one from Emmy here, and Emmy asks, what brings you most comfort when you feel down about this current universe and the climate crisis?
Well, first of all, I take a look at the big picture. When I write down an equation, it's comforting knowing that somebody on the other side of the Milky Way galaxy, some alien with a different script, a different time frame, whatever, is writing down that same equation that I'm writing down. Now, if you're an expert on Shakespeare, more power to you. However, you can't talk Shakespeare to an alien on another side of the galaxy. They may have totally different values, totally different outlook than the person who wrote Shakespeare. While if you are a physicist, you know the universality of the whole thing. Now, I tend to be an optimistic about these things. General Dwight Eisenhower, helped to win World War II, once said that pessimists never win wars. Wars are only won by optimists. And therefore, I tend to be optimistic about things because, if you take a look at history, I think the smallest unit of history is the decade. Anything smaller, you get random fluctuations. When you look at human history decade by decade, then you begin to understand the enormous progress that we've made. You realize, I looked this up, for most of human history, life expectancy was about 30 years of age. Life expectancy, by going to the graves of our ancient ancestors, going to the ancient manuscripts, 30 years of age. You were born, you got married, and then you died. In other words, life was a bitch. Today, we live in a world where life expectancy is hitting 80. So if you take a look at history as the smallest unit being the decade, then you have optimism. Now, global warming, of course, is a real threat. So is nuclear proliferation. So is a potential pandemic. So these are three things that could destroy civilization on the earth, but there's some hope in the horizon. What's wrong with solar power? How come we don't have solar power engines everywhere? People forget that the bottleneck is not solar power at all. It's the battery. When the sun doesn't shine, the winds don't blow, solar is useless. So inventors are now trying to invent the super battery. That's the bottleneck for the solar revolution. People forget that. Once we develop a super battery, then we'll be able to drive down the cost of solar so that it's much cheaper than fossil fuels. And then much farther down the line, fusion power is a possibility. The power of the sun. Now, not fission power. Now, when I was in high school, Edward Teller, the father of the hydrogen bomb, was my mentor and advisor. When I graduated from Harvard, he offered me a job to design hydrogen warheads. I said no. I said, I do not want to design hydrogen warheads because I want to work on something even bigger than that, the Big Bang. Well, fusion power is like the power of the sun on the earth. What drives fusion power? Seawater. Hydrogen from seawater is the fuel for fusion power plants. What's the catch? They don't exist yet. But within 10 years or so, we hope to get a prototype off the ground in France. And that could be the ace in the hole. Not for today, but by mid-century, that could be our ace in the hole.
Optimistic. I like that. To go back to one of your previous books, Masoto asks, in Physics of the Impossible, you talk about quantum teleportation, with information traveling from atom A to atom C, and this would be done by introducing an atom B. Could you explain a little bit more about how this would work?
It turns out that teleportation, sort of like in Star Trek, is possible, but we're not sending Captain Kirk from point A to point B. We're sending the information to build Captain Kirk from point A to point B. So it's sort of like getting a model kit, but only sending the instructions, rather than the actual kit itself, and you have to assemble the kit. Now, we do it using quantum entanglement. Now, remember, quantum entanglement does not go faster than the speed of light, but it does go very fast. It does go at sublight speed. That you can use to transport information from point A to point B, and it's been done now. The Chinese even send it into outer space. That is a detector on the Earth was shot a beam to a satellite in outer space, and that information was teleported into outer space. Now, I think that we're going to go back to the moon probably in 2 to 3 years, and we'll probably do an experiment to send information to the moon from the planet Earth. Now, again, this does not mean you can send a telephone message faster than the speed of light, but it does mean that pure information, the information of atoms, can be sent faster than the speed of light. So far, we've teleported photons of light and also atoms, I think cesium, have been teleported using this method, but it's not yet ready to teleport a human. Humans consist of trillions upon trillions of atoms. At the present time, we can only teleport one atom at a time. So sorry about that.
I've got a good one from Michael here because you've been talking about such amazing things. And Michael's question is, what are the odds of humans surviving long enough to better understand these wonderful mysteries of existence?
Well, we're reaching a danger point. If you rank civilizations by energy, a type 1 civilization would be planetary, like Buck Rogers, Flash Gordon. They control the weather. A type 2 civilization is like Star Trek. They control the power of the sun. Solar power is what they use there for their engines. Type 3 civilization is galactic, like Star Wars. They roam the galactic space lanes. Now, on this cosmic scale, what are we? Do we play with the weather? Do we play with the sun? Do we roam the galaxy and the galactic space lanes? No, we're type 0. We get our energy from dead plants, oil and coal. But we are about, you do the math, we are about 100 years from being type 1. For example, what is the internet? The internet is the first type 1 technology to fall into this century. What is the language of type 1? Already, English and Mandarin Chinese are the two major languages on the internet. We're seeing the beginning of a type 1 fashion, Gucci, Chanel, a type 1 sports, the Olympics, soccer, type 1 music, rock and roll, rap music. We're seeing the beginning of a type 1 civilization. Now, what can go wrong? 3 things can go wrong: nuclear war, a pandemic, and global warming. And it's not guaranteed that we will reach type 1. We might blow ourselves up. One day when we have rocket ships and visit other planets, we may find that their atmospheres are too hot because they had global warming. Their atmospheres are radioactive because they had nuclear war, or there's germs everywhere. They had a pandemic that destroyed their civilization. So the danger period is now. Now we have the ability for the first time in human history to make a transition from type 0 to type 1, but we may blow ourselves up in the meantime. So that is a warning that we could be entering paradise if we can only control our backward tendencies.
I've got a question from Jeffrey here, and Jeffrey asks, what are your recommended books on mathematics to comprehend your book?
Well, I'll be blunt. The books I write, even school children read. I write for myself as a child, because when I was a child, I wanted to know about the fourth dimension. I wanted to know about antimatter. I wanted to know about all these things I read in science fiction, but nothing. There was absolutely nothing in the library about what I read in science fiction. So I said to myself, when I grow up, I'm going to become a publishing theoretical physicist, and I'm going to keep my promise to myself as a child. I'm going to write for myself. I'm going to write for the child that was so frustrated going to the library, trying to find out about the unified field theory, only to find nothing, absolutely nothing in the library. Now, if you really want to know the math behind what I do, it takes 5 years of 5 years of calculus. You have to have differential calculus, integral calculus, multivariable calculus, and then Lie groups, then topology, 5 years of calculus. And I've written books for grad students. If you are a PhD student, get my book, Introduction to Superstrings and M Theory, which gives you the mathematics of string theory. But it's not for the faint-hearted. It requires 5 years of calculus.
I'm seeing a lot of questions here about dark matter, and I know that you already touched on that earlier, so I'm going to kind of wrap these questions into one here for you. I think you already touched on this question, which is, are we certain that dark energy exists? And if so, what is your theory on dark energy? Then there's a follow-up question from Morgan, and that's, do you think it's possible that there's a link between dark matter and occurrences in nature like genetic mutations and thus things like identity and cancer?
Well, first of all, dark energy and dark matter are two different things. Dark matter holds the galaxy together. It's invisible. If I had dark matter in my hand, it'd be invisible, but it would fall right through my fingers, go right through my fingers all the way to China on the other side of the earth, turn around in China and come all the way back to New York City where I am now. That's dark matter. Dark energy is even more mysterious than that. It is the energy of nothing. Even nothingness has energy associated with it, and it is pushing the galaxies apart. When people hear about the expanding universe, they say, well, why is it expanding? It's anti-gravitational. That's right. Anti-gravitational dark energy is what is pushing the galaxies apart, and that's why the universe is dying. The laws of physics are a death warrant for the universe, unless we leave the universe, as I mentioned, because of the fact that dark energy pushes the galaxies apart. Now, what are they? I think that dark matter is nothing but the next octave of the string. That's a theory, not proven at all. There's no proof for any of these theories. This is still speculation, but speculation based on all the facts as we know them. So dark matter, we think, could be the next octave of the string. Dark energy, we think, is the energy of nothing. And unfortunately, even in string theory, it's difficult to calculate that number from first principles. But these are the two great mysteries. Now, what about matter? Hydrogen and helium make up 4% of the universe. 96% of the universe is dark. 4% of the universe is stars. What about us? We make up 0.04% of the universe. We are the oddballs. We're the oddballs. Most of the universe is dark. The rest of the universe is stars, and we only occupy about 0.04% of the universe.
Well, I think we're running out of time here, but I think that there's a good question from Randy here that might be a good note to end on, and that is, will physicists just go home after the models are unified, or are there other inviting questions to test and study?
Well, people often ask me, are you going to be out of work? Are you going for the unemployment line? Once you find the theory of everything, there's nothing left to do, right? Nope. You see, I think the universe is a chess game. And our destiny as a species is to find the rules of chess. For 2,000 years, we figured out how the pawns move, we figured out how the bishops move, but our final destiny is to find the God equations, in other words, the rules of chess, and then become grand masters of chess. That, I think, is the destiny of humanity. So there's plenty to do, because when matter gets together, all of a sudden emergent phenomenon emerge. Life, love, consciousness could be emergent phenomena that are not in the rule book of chess. Just because you have a rule book of the rules of chess does not mean that you are a grandmaster, does not mean you know all the strategies and all the different ploys that grandmasters know. That's what we will become. We will end the phase of figuring out the rules to become grandmasters to discuss emergent phenomena like love, like beauty, like where are we from?
That's wonderful. And I think we're out of time, but I just want to thank you so much for joining us tonight. That was wonderful. I know I learned a lot. This isn't my area of expertise in any way, and that was such an amazing, helpful discussion. I hope everyone else out there feels the same way. Next time, I hope we're able to welcome you back to the store instead
Mhm.
of virtual, but this has been wonderful. And I want to thank everyone out there for joining us. Please do purchase a copy of The God Equation online at powells.com. Check out our other upcoming events. Until then, have a wonderful night, everyone.
Okay, it's been a real honor and pleasure.
Thank you. Have a good night.